Hello and welcome to Non-IITIAN. This is the second lecture on the group theory series. And in this lecture, we will be particularly talking about cyclic groups. So our precise, the details will be on cyclic groups. But nevertheless, if time permits, we'll give some brief insights into abelian groups as well, in at least the fundamental structure. Okay, so in the previous lecture we had discussed, or rather introduced, the notion of cyclic groups. Here we are going to do with more formality. So yeah, so this is lecture 2. Before that, let me just briefly explain what a subgroup is. Okay, so definition of a subgroup. So let G be a group, then a non-empty subset of H of G is called a subgroup of G if H is a group with respect to the same ambient operations, that is the operations on G. Okay. So immediately from the definition itself, it's clear that the set of integers is a subgroup of the set of rationals, which is a subgroup of the set of reals, which is a subgroup of the set of complexes with respect to the usual addition, right? Yeah. So you can find out more and more subgroups more naturally, as we'll see in case of cyclic groups at least. And in fact, there are a lot of ways to construct out subgroups from simpler structures. Nevertheless, something which we do not require at this point, but you can obviously check whether a given non-empty subset is a subgroup or not with respect to the subgroup test, which is quite easy to observe. That is, if H is a non-empty subset of G, then H is a subgroup of G. This is the notation we would be using to denote subgroups. If and only if for every AB in in H, AB inverse is in H. And let us give a very quick proof. So proof, that is, this particular checking is sufficient to check whether H is a subgroup or not. Now if H is a subgroup, so it's a group in itself, so this will rightly hold. So all we need to do is to check the converse of it. So what do we need to check for H to be a group? We need to check that it's closed, and then so we do not need to check whether the operation is associative or not, because associativity is solely dependent upon the operation. It is not dependent on what set or what the set from which the elements we are considering. So all we need to check is that whether the identity is in H, whether it's closed under inverses, and whether it's closed under the operation itself. But that's quite easy to observe from here, as if B is in H, then by hypothesis B times B inverse must be in H. So that implies 1 must be in H. So now again, if B is in H, since 1 is in H, so 1 times B inverse, which is B inverse, must be in H. And lastly, if A is in H and B is in H, but then B is in H would imply B inverse is in H. But then from hypothesis we would see that A times B inverse whole inverse is in H. But that would imply AB is in H. So it's closed, it's closed under inverses, and it's also containing the identity. So this rightfully helps you to check whether a non-empty subset is a subgroup or not, with just one typical check, and that's it. So we are not going to get involved into a detailed discussion of subgroups because it's quite elementary from every sense. When we will be requiring some important notions with respect to subgroups, we will eventually get through that in terms of examples. But what we need to define now, or rather deal with more formality, is cyclic groups. So definition: first we need to define how to formally write down exponents of certain elements in a group G. And again, I'm mentioning it out. The usual sense to deal with groups conventionally is to treat them as multiplicative. Okay, so let G be a group, and let small g be an element of capital G. Then we define G to the power n as, so we just take G and operate it n times with itself, just as we do in case of any multiplicative set. Typically, if n is a positive natural, we take it to be 1 if n is 0, and we take it to be, G inverse to the power n in the most usual sense, or rather I can just write it as G inverse operated with itself n times if n is negative. Okay, is it clear? Fine. Yeah, so this is how we denote the exponent or the power of an element in a group. And by the closure property of every group, we are sure about the fact that if G is in, so if G is in a group G, then G to the power n also resides in G for every integer n, right? Fine. Now definition: a group G is said to be cyclic if there exists some element G in G such that G is generated, or rather G is this particular collection. So 1G, yeah, I should formulate it like this. So G is contained of all these elements and only these elements. Okay, and this particular set is what we denote as this. So it is more formally considered as the group generated by small g. In fact, there is a more general notion of groups being generated by a collection of elements, but again, that is something which we do not require at this point. In fact, I can define it. Okay, so let me just say it. So suppose S is a subset of G, G is any group, then by this particular notation, we mean all these elements. So a1 to the power epsilon 1, a2 to the power epsilon 2, so on and so forth, ak to the power epsilon k, such that a1 till ak are elements from S, and each epsilon I is plus or minus 1 for every I. So this is called the group generated by S, and it's obviously a subgroup of G. Furthermore, this is in fact the smallest subgroup of G containing S. And observe that if S is just a singleton set A, then the group generated by S is nothing but the cyclic group generated by A. Okay, fine. Now this is quite easy to observe that every cyclic group is abelian, right? So every cyclic group is abelian. Right? This is quite clear from the definition itself. Okay, examples we were discussing in the previous lecture itself, that is Z is a cyclic group. Z is a cyclic group. A non-example would be Q is not a cyclic group. Is not a cyclic group. In fact, there's a stronger notion in Q, that is every finitely generated subgroup of Q is a cyclic group. And what do we mean by a finitely generated subgroup? So by that we mean a subgroup generated by some set S, where S is a finite set. That's it. Okay, every finitely generated subgroup of Q is cyclic, and Q itself is not a cyclic group. And the very basic idea behind claiming this is the following fact, that if q is generated by some element p over q, for example, then n times, because it's additive, so yeah, so you should be familiar with the way we try and denote the additive structure as well. So you could have written this as n times g for n in z in the additive notation. Okay, I hope it's clear at this point, so I won't be able to repeat it every time, but I hope it's you are getting familiar with this. So here we have additive notion. So what does this mean? This means that n times p over q must be obviously be in q, n plus 1 times p over q is obviously in q, and n plus 1 uh, times p over q plus n times p over q by 2, this is also a rational number, right? This also must be in q. So what is this basically? So this is basically rather I can do it, I can take minus here, so it's just p by 2q. But if it's of the form some k times p over q, what does that mean? That means k must be equal to 1 over 2, but it's not an integer, right? Clear? So every element in q is not multiple of p over q, so hence it cannot be cyclic. Fine. Okay. Yeah, in fact there's a very it's a very important result in group theory as well, that r plus, or rather in r plus, a subgroup is either cyclic or dense topologically. So I'm assuming that we do not know topology on whole, but nevertheless, if you ever come through topology, then you should be able to understand what dense means. Okay. Yeah, fine. Yeah, let's continue. So now I would obviously define what is the order of an element. So order. Okay, so let me define it. So let g be in g. The order of g, which we typically denote as order of g, is the least positive integer n such that g to the power n is equal to e if rather yeah okay, if such an n does not exist. If such an n does not exist, then we take order of that element to be 0, and in some books you'll also see it to be infinity, but we usually work with 0 because it's in some sense more meaningful. Now observe the following lemma. So if g to the power m is equal to e equal to 1, okay, so I just mistakenly wrote it to be e, I'm sorry. Yeah, so we are working with the conventional notation 1. So if g to the power m is equal to 1 and g to the power n is equal to 1, we are working in an ambient group G, so I'm not mentioning that over and over. Then g to the power the GCD of m and n is also equal to 1. So this is the way we denote GCD, and I hope you guys know what the greatest common divisor of two integers typically is. Proof, quite easy. We can use the Bezoar lemma. We know that there exists an integer d such that sorry, I'm extremely sorry, I should have written, if the GCD of m and n is d, there exists x and y integers such that m times x plus n times y is equal to d, right? So this is what we a very important result in number theory called the Bezoar lemma. But from here what we can say, so from here we can rightly say that then g to the power mx plus ny is equal to g to the power d, but this implies g to the power d is equal to g to the power m whole to the power x plus g times g to the power n whole to the power y, but these are 1, right? So there's a very crucial role between algebra, the typical algebra you study, and the typical number theory you probably have studied previously or you will study eventually in future. And there's a very a very hybrid field which is very spectacular in studying mathematics, which is called the algebraic number theory. And algebraic number theory is typically uh, played the most important role in proving the Fermat's last theorem, where we typically use elliptic curves to prove the fact. Yeah, nevertheless. Okay, so let us move on to the next important proposition in this context. So if order of g is less than rather is equal to n, which is a finite number, then g to the power k is 1 if and only if n divides k. Okay, so proof, and the proof is quite simple. See, if n divides k, then that would mean I can write k as some n times m, but that would mean g to the power k is equal to g to the power n whole to the power m, which is 1. So it's quite clear. Conversely, suppose g to the power k is equal to 1. Now, by Euclidean algorithm, or rather by Euclidean division lemma, we know that every two integers can be written in the form of, I can write k as some n times q plus r with so we are dealing with positive integers in every sense at this point, right? So with r greater than or equal to 0 and this is less than n, right? So this is the typical Euclid's division lemma. But from here what can we conclude is that, so this implies that k minus nq is equal to r, and this implies g to the power k minus nq is equal to g to the power r. But from here we have g to the power k times g to the power n whole to the power minus q is equal to g to the power r, but g to the power k is 1 and g to the power n is also 1, so I have 1 is equal to g to the power r. But that's a contradiction, right? No, that's not a contradiction, I'm sorry. But that implies r must be 0, as if r is non-zero, then r is a smaller positive integer such that g to the power r is equal to 1, which contradicts the the minimality of n, right? Because n by definition was the smallest positive integer for which g to the power n is equal to 1. So r becomes a smaller positive integer which can't exist. Right? So the only possibility for r is to be 0, but once r is 0, what we know that is n divides k. And so we are done with the proof, right? Is it clear? Okay, fine. Now, so this actually plays a very crucial role in the following sense, that there is something called a Lagrange's theorem. So I am not intended to prove this at this point. We will prove this in the next lecture. And Lagrange's theorem is a point where we need to deal with subgroups on a more detailed note. But the Lagrange's theorem typically says that if G is a group and H is a subgroup of G, then the order of H divides the order of G. And the converse of this is not necessarily true. That is, every divisor of the order of G must not necessarily correspond to a subgroup of G. Okay, there might exist, in fact they surely exist, there are lots and lots of examples where the converse of the Lagrange's theorem does not hold. it holds typically in abelian groups, as we'll see later, by the fundamental theorem of abelian group, by the fundamental structure theorem, but it does not hold true in most groups, to be honest. Okay, so this is called the Lagrange's theorem, and what this typically gives is the following. That is, so this results in the following fact, that if G is a group, so I can just write it as a proposition. If G is a group, finite group, okay, so we are dealing with finite groups, right? Because whatever we are dealing here, since we are essentially working with the cardinality of a group, I should obviously consider it to be a finite group. So if G is a group, finite, and G is an element of G, then the order of G must necessarily divide the cardinality of the group. And the proof is pretty simple, because I can take H to be the subgroup generated by G, which will obviously be a subgroup of G. But then, as we were seeing in the previous lecture, the order of H will be the order of G, right, which divides the order of G by the Lagrange's theorem. But since the order of G divides this, so this means that G to the power cardinality of G must be 1. Okay, so I was intended to prove this, so then is equal to 1. Okay, and a very useful result of this is the Fermat's little theorem, which says that if A is an integer, P is a prime, such that the GCD of A and P is 1, then A to the power P minus 1 is congruent to 1 mod P. And how we can prove this, I'm just giving a brief hint to it, because we have not delved into much that deeper notions. But what we can typically deal from here is the following, that if I consider ZP the group modulo P, then so it's a group with respect to addition modulo P, right? So then ZP cross, which is nothing but ZP except the element 0, is a multiplicative group, of order P minus 1, and hence for every A in ZP cross, A to the power order of ZP cross, which is P minus 1, must be congruent to 1 modulo P, right? So it must be equal to 1 in ZP, but that translates to the fact that it's congruent to 1 modulo P, right? Is it clear? So it essentially helps you to prove the Fermat's little theorem. Okay. So how are we able to say that ZP, so why are we so sure about the fact that ZP cross is a group of order P minus 1? Because we are sure about the fact that ZP is a group of order P. And why is that? So we'll come to that now. It says the following. Okay, so theorem, let G be a cyclic group generated by some element G, then 1. If the order of G is n, finite, then the order of the group G is n exactly. So this proves that Zn has in fact this was quite trivial from the definition of Zn. I did not need it to be of having order P minus 1 by proving it to be cyclic. Nevertheless, this is something important. So number 2, if the order of G is 0, then G is isomorphic to, so I would be rightly trying to prove that G is isomorphic to Zn. Okay, So G is isomorphic to Zn, and here G is isomorphic to Z. And in the course of the proof, we'll explain what isomorphism is. So let me just rightly explain here. So there is a notion of a homomorphism within groups. So let me just define it. So let G and H be groups. A function phi from G to H is called a homomorphism if it's a function which preserves the operations in the groups. If for every G for every X and Y in G, phi of xy is equal to phi times X, phi times Y. Okay, so for a more general notion, let me just denote the operations of both the groups to be different. So then this should be this. Okay, so it preserves the operations of the groups. So it preserves the internal structure of the groups up to some sense. Okay, right. Yeah, so bijective homomorphism is what we call an isomorphism. A bijective homomorphism is an isomorphism. Okay, some quick exercises in terms of homomorphism. So exercise, we define, so given phi from G to H a homomorphism, we define kernel of phi to be the collection of all those elements G in G such that G is mapped to the identity element of H. So it's the identity element of H, and the image of phi is denoted as all the possible images of the elements in G. So that G is in G. Okay, so the first exercise is as follows. So 1, prove that phi is injective if and only if the kernel of phi is the trivial subgroup. So it's a trivial subgroup, right? The group generated by 1 in case of the multiplicative convention, and in case of the additive convention, the group generated by 0 element is always a subgroup. The other trivial subgroup would be the whole group itself. And 2 is a more simpler proof that image of phi is a subgroup of H. Okay, yeah, so try and prove these two things, because these are pretty trivial exercises, so I won't be considering them as lemmas afterwards when we will be dealing with homomorphisms in more details, but these are good exercises. So yeah, so now let us talk about the proofs of the proposition of the theorem. So number 1, so what is the group G in this case if the order of G is finite? So it's 1 G, G squared, so on and so forth till G to the power n minus 1. Now what we need to do is that the only thing which we need to prove here is that two elements are distinct here, nothing else, right? Because the rest of the structures are automatically there from definition. So let G to the power K and G to the power J be from capital G, and obviously we choose them not to be distinct. Okay, no, I need to prove them to be distinct, so I need to take K not equal to J. Then what can I claim? So then if, so let me just remove all these assumptions. Okay, suppose G to the power K is equal to G to the power J. So this implies that G to the power K minus J is equal to 1. But what does this imply? So the order of G is n, so this implies that n divides K minus J, which implies that K is congruent to J modulo n, right? But since K and J both are less than n, that should essentially imply that K must be equal to J, or that K minus J is 0. Okay, So we have proved that, so this implies that the order of G must be exactly equal to n. Okay. Now how does the isomorphism take place? So let phi be a map from Zn to, or let us take a map from G to Zn by taking a to the power r mapped to r. Okay. So what does happen? So is it well defined first? It's obviously well defined, right? Because if a to the power r is equal to a to the power j, we have just proved that that should imply r is equal to j. So this implies phi is well defined. Also, if also injectivity holds quite immediately from here, that phi is injective. In fact, you can try and prove what is the kernel of phi. So the kernel of phi is collection of all those a to the power r such that phi of a to the power r is equal to 0, right? So 0 is the identity element of Z, and you should be sure about that. So that is a to the power r such that r is equal to 0, but that's just 1, right? So that implies that phi is injective and phi is surjective from definition. Phi is surjective from definition. So phi is a bijection, but is phi a homomorphism? Let's see. So what is phi of a to the power r times a to the power s? So it's phi times a to the power r plus s, but that's exactly r plus s. But then that is nothing but phi of a to the power r plus phi of a to the power s. So which implies phi is also a homomorphism. Fine. And hence an isomorphism. Right. So we have proved this, and we need to prove 2. But that's quite immediate itself, because so I need to prove that G is isomorphic to Z. And for that, what can I do? I can take a map phi from G to Z by the same thing. So I will take phi a to the power n and I'll map it to n. Okay. Now observe the very simple fact here that in G, which is an infinite cyclic group, so with order of G to be 0, G to the power r is equal to G to the power s. Okay, so this is an exercise. What should be what? Yeah, so okay, so let us go through the course of the proof. I do not want to give so many exercises. It will make the course very rigorous, or rather typically very difficult. So then what happens here? So yeah, so then is phi well defined? It's quite easy, right? So if a to the power n is equal to a to the power s, what does that mean? See, so the exercise which I was trying to give is the following. Suppose a to the power r is equal to a to the power s. That implies a to the power r minus s is equal to 1, right? So that would imply order of a to the power r minus s must be equal to, or rather, what can we conclude from here? See, we have assumed that the order of a is not finite, right? In the usual sense, that is, there is no finite positive integer such that a to the power n is equal to 1. But there is some integer we are getting r minus s to be equal to 1. Right? So by assumption, this should imply r must be equal to s, or r minus s must be equal to 0, since order of a is 0 and there does not exist n positive such that a to the power n is equal to 1 by assumption. So this implies r is equal to s. So this in fact proves that phi is well defined, and in fact this was the exercise which I was trying to give. Okay. Now is phi injective? So phi is injective by definition itself, and phi is surjective also by definition itself, and phi is homomorphism also by the same steps. Phi is clearly a homomorphism. So you can fill in the gaps. These are pretty easy proofs. Homomorphism. Hence, G is isomorphic to Z. Fine. Is it clear? Okay. So now let us get more involved in the cyclic groups. So now, so definition, let G be a cyclic group G in G is said to be a generator, or in some books you will also find the term a primitive element, a generator of G if I can write G generated by this. That's it. Okay, that's it. Now the question is that whether a cyclic group will have a unique generator or not. Okay, so for that, observe the following example. That is, suppose I take Z5. So Z5, which is 0, 1, 2, 3, 4, right? So it's a cyclic group with 5 elements, and it's quite clear that Z5 is generated by 1, right? But observe that it's also generated by 2, and it's also generated by 3, and it's also generated by 4. So what should be 2? So let us just come up with this. So 1 times 2 will be 2, 2 times 2 will be 4, 3 times 2 will be 6, which is 1 modulo 5. 4 times 2 will be 8, which is 3 modulo 5, and 5 times 2 will be 0. And similarly, you can see that 3 and 4 also generate Z5. Similarly, you can see that if I take Z4, which is 0, 1, 2, 3, then Z4 is generated by 1, obviously, but it's also generated by 3, and it's not generated by 2, because what this set typically is. So it's 1 times 2, which is 2, 2 times 2, which is 4, which is 0, and 3 times 2 is 6, which is again 2. So it just cycles around 2 and 0. So it's not equal to Z4. And some interesting thing which you can observe from here is that 3 and 4 is 1, that is 3 is co-prime to 1, co-prime to 4, and 1 is obviously co-prime to 4. And here all these 4 elements were co-prime to 5. So there is something to deal with these elements which are co-prime. Which brings us to the, okay, so I'm exhausted of the pages, I'm sorry. Yeah, so let me, okay, so fine. So let me just complete this in the new pages. Okay. And then from the next lecture onwards, I'll remove the other pages. Okay. So let us move on to the following theorem. So let G be the group generated by G with order of G, cardinality of G is n. So order of group is same as the cardinality of the group. Okay. Then G to the power k is also a generator of G if and only if the GCD of k and n is 1. And I'm not going to go through a detailed proof of it. You can find the proof in any standard proof. For example, you can find the proof in Herstein, or you can find the proof in Gallian. So I'll recommend Gallian at this point. Okay, Joseph Gallian, probably the author name. But I'm just giving a hint towards the proof. See that the order of G to the power k should be the smallest m, such that G to the power k whole to the power m is equal to 1. But that implies G to the power k m must be equal to 1. But since order of G is n, because the cardinality of capital G is n, so that would imply n must divide km, right? But then observe that, but then the smallest such m is n over the GCD of k and n, because GCD of k and n is the largest common divisor of n and k. Okay. So therefore, what we conclude from here is a certain corollary. So corollary that G to the power k generates G if and only if k and the order of G are co-prime. So now let us get back to the previous example. So here you can observe it, that what is the order of 3. So you can just see that 1 times 1 times 3 is 3, 2 times 3 is 6, so it's 2, and 2 and 5 is 1. So we had misinterpreted that the element must be co-prime to 5 in a sense, but it's typically the order which needs to be co-prime to the number of elements in the group. So that should be made sure. I hope it's clear. The final thing which we will be discussing here is something a pretty non-trivial, which we do not usually, get involved to when we study groups for the first time, but I wanted it to be included, which is called the exponent of a group. So definition: the exponent of a group G, which is denoted as exp of G. So this is basically the so it's is the smallest positive integer n such that g to the power n is equal to 1 for every g in G. Okay, is it clear? A quick exercise: prove that the exponent of a group is the LCM of the orders of all the elements in the group. Obviously, if it exists. Fine. Okay. In fact, something which we can also see and observe, that in fact, if G is finite, then the exponent of G must necessarily divide the order of G. And the proof again follows from Lagrange's theorem, that is, the order of G divides the cardinality of G for all G in G. But then by definition of LCM, so the LCM of all the order of G must again divide the order of G. So that would imply that the exponent of G necessarily divides the order of G. Now there exist groups which are infinite but with finite exponents. So example, an infinite group with finite exponent. Yeah. So what you can do is that you can consider Z mod 2 and you can take infinite direct sum of it. So with component wise operations, these are called direct products with component wise operations. Okay, that is, suppose you have a1, a2 and so on modulo 2, so b1, b2 and so on. This is nothing but a1 operated with b1, then a2 operated with b2 and so on. And this has a natural group structure, induced from the group structure of Z2. So it's clearly an infinite group, but its exponent is 2. Clearly, right? Because 2 times any element a1, a2 will be 2 times a1, 2 times a2 and so on, but all of these will be 0. Clear? Okay, so that's all for this lecture. In the next lecture we will be talking about some important subgroups, or we might be talking about homomorphisms and isomorphisms in more details. So meet you guys in the next lecture.